Welcome to the session. Greeting of the day. In the previous classes, we are on the discussions of the TIG welding process and their working principles, advantage, applications. In continuous with that, so operating variables, the welding current and then arc voltage, welding speed, shielding gas, electrode type. One after the other are most important types here. So TIG torch setup. You see? So likewise, we know. So this is a TIG torch, and we have the electrode extension. See, this zone is electrode extension. How far it is, and this is the strikehouse region coming out from the nozzle. But this is the electrode extension coming out from the electrode holder. So that is what electrode extension. So now, if the electrode extension is too large and keep on extending this electrode extension too wider than the other gap, arc length increasing likewise, what happens? Overheating of the tungsten inclusions. Because this is tungsten, this is going to generate heat. When it is exposed to the plasma zone is here, this zone is a plasma zone. When it is exposed to the plasma zone, it is also heated. The electrons should travel from here to that end. It does not mean it should come here, come out from those correct point itself. It can able to reach that positive process. But what happens? It should not the electrode extension to be minimum, not too large. If too large, tungstens will make overheating. Now I am not coming out. I am keeping here itself. Very minimum point I am keeping. What happens? Low electron emission. Electron should emit. Heat should be there. Sufficient heat to be there. If I am not doing such cases, what happens there? See, this electrode, instead of this, I am supplying here. It is not at all exposed to the plasma zone. Then where is that heat will form? Where is that 70% heat will there? Where is the electron will come out? Electron won't come out. So electron emissions will not be there. Shielding gas requirement. In this shielding gas requirement, you see, we have to protect the weld. That is our main agenda. We have to protect the weld. When we have to protect, it should start pre and it should stop post. So welding has happened in this zone. It started the red layer. It is started here. Welding done and comes down. But where I am supplying the shielding on and off, pre-flow I am heaving. See, I have started shielding protection first started. Gas protecting atmospheric contamination are stopped, and then heat supplied for welding. First its protection started, and then I am starting the welding, and then I am completing the welding. After that, for a while I am not stopping the shielding. Later I am stopping the shielding after a small solidification process takes place. Then only atmospheric contamination not come into the picture, otherwise it will come there. Now, if the shielding gas is too low, what happens here? Red color belongs to atmospherics. So this, if it is too low, it's not sufficient to protect this zone. What happens? There are some atmospheric contamination will come into the picture. Now, if this is too high, what happens? This blue color will cause the turbulent actions at the center. Turbulent action should not be formed. Turbulence also, it will affect the flow of electrons. Therefore, turbulence also should not form. Too low is not recommended. Too high shielding also not recommended. The optimized one. That comes by practice. We want to talk about this common shielding gases. In this, normally in the all inert gas welding process, we are using the helium, argon, mixture of these two, helium and argon, nitrogen and CO2 we are normally using. Why we are using selection of these gases depends upon metal to be welded and its thickness, how far it is thickness, heat generation, criticality of the application and economics. We are using these things depending upon this. We want to know about the properties of this argon and properties of this helium. Then we can able to use this argon and helium appropriate places. So argon having the tendency of high ionization potential is 16 electron volt. It's measured, it's lesser heat as compared to the ionization potential of the helium of 25 electron volt, which gives high heat generation. In helium, when we are using the helium, it generates a high heat. But in the same cases, when I'm using this ionization of argon, it generates a less heat. You see, less heat is generated. The moderate arc stability, which is lesser than that of helium. And then one more thing I want to tell you here, it contains a moderate thermal conductivity also. It means transfer heat from the arc to base also moderate. Transfer of heat from the arc to base, the gap, this also is moderate when we are using the argon. Here it is very less. But at the same time, what happens, in this side you see, it has high thermal conductivity. The helium having high thermal conductivity, so it can absorb more current and it can able to withstand more arc stability will be there. Conductivity directly related to the stability. If there is no conductivity, how this gas, as like gas, it's also restricted the electron flow. You should be have the conductivity, then only the electron will come and impinge over there. Therefore, it having the high thermal conductivity than that of argon. So what happens? Transfer of heat from the arc to base is effectively transferred. So here, high heat is generated, helium is helpful. After heat generation, arc to be stable, which is to be transferred to the workpiece. Heat generated, helium good. Transfer of heat to the workpiece, helium good. Mark it in green. But here you see, heat generation moderate. At the same time, transfer of heat to the workpiece, conductivity is low, therefore that is also moderate here. Where we are using, so therefore moderate welding speed is here, but here you can see increased welding speed, If this heat is generated, our work is simplified. Easily we can melt, deposit and move to the another location. Therefore increased welding speed. But when we are using the argon, what happens here, you see, it is a moderate welding speed as compared to all these things. These two points we have mentioned. Now the third point, it is heavier also. Argon is heavier than that of helium. What happens then? Whenever the shielding gas is released, it tries to comes down. Whenever the helium is released, it is lighter, it tries to goes out. These facilities we should use. Already this point I have told you. So helium can be utilized in the overhead positions, argon can be utilized in the downhead positions. So what happens? It is heavier, that means 10 times heavier than helium and 1.3 times heavier than air, normal air. Argon is heavier than that of air. So what happens there? Less quantity required for shielding. It means when we are doing the welding process, the turbulence will not happen. Whatever this flow is generated, it keeps on going downwards. If around the electrode, if the shielding gas goes on downward, there is no disturbances. It's perfectly shielding around the atmospheric environment. Remaining part we can do, but protection is needed. So at the same time, when I'm using the helium, whenever it is released, it tries to move upward due to its weight, less weight of helium. And then here there is no protection because whenever it is released, it tries to move up. Then obviously atmospheric contamination will be there in between this arc gap. Therefore, heavier argon is utilized for downhand positions. See, therefore it is utilized in the downhand positions. I have written here, utilized in the downhand positions. But there the same pattern I am using in this side also. See, it is lighter. How many times? It is 10 times lighter than argon. I have mentioned here, it is 10 times heavier than helium. Here I have mentioned 10 times lighter than argon and 1.3 times lighter than air. What happens? If it is lighter than air, it is try to move upward like a helium balloon. We have heard helium balloons. So why it is helium balloons are filled with helium? It is going upward. So that is a helium balloon. The same pattern is lighter in weight. Therefore, it moves upward than that of air. So that we are using for the welding purpose also. Where you are using, it is moving upward. It means protection is given there. I want to weld here. Air shielding is released there, and it is completely, it is lighter in weight. It is trying to move up, but here the job is there. but it is blocking. But what happens? It is also pushing upward. So good shielding will be there around the weld zones. So atmospheric contamination will not happen at the overhead portions. Therefore, I can able to preferably use it for overhead portions of this helium. So 3 points we have concluding here: ionization potential, thermal conductivity, and then lighter in weight. So these are useful for good arc stability, heat transfers, and then overhead portions and welding speed also. So this will be useful for helium. These are the properties of argon: moderate stability, moderate heat generations, and then 10 times heavier, therefore useful for the downhand positions. So similarly we have to see about this CO2 also. So this is what the ionization potential of helium is 25 is higher than that of argon. Therefore application of helium is shielding as results in higher arc voltage are generated. When this high heat is generated, high arc voltage is possible to generate. Therefore the arc characteristics is found to be different in the argon and helium. The welding current for argon corresponding to the lower arc voltage is usually around 500 amps, while that of helium occurs at around the 150 amps. Arc efficiency: helium has a higher thermal conductivity. Now only we have seen that helium has a higher thermal conductivity and then argon, and hence they effectively transfer the heat from arc to the base material, helps to increase the welding speed. This we know. Now it is helium is increasing the welding speed. Arc stability, now what we have talked there. Helium is found to be offer more problem related to the arc stability. This behavior is primarily due to high ionization potential of helium than that of argon. High ionization potential means the presence of fewer charged particles between the electrode and the workpieces required for initiation and maintenance of the welding arc. This we know. Flow rate. How much flow rate now we should give? This point we have not talked there. How much flow rate we should give there? Argon we need, see, 1.78 is liter. It's about 1.33 heavier than that of air and 10 times heavier than that of helium. This point we have already seen. This different in density of the air with the shielding gas determines the flow rate of the particular shielding gas. How much? Therefore, helium having 1.3 times lighter than air, upcoming immediately turbulence manner may happen. So it is trying to move upward direction. Therefore turbulence will form and contaminations will be there. So helium to be given higher, it means if we are giving in the downhand positions, helium shielding to be given higher force, higher liter per minute has to be given. See? Therefore effective shielding of flow rate, helium has given 22 liter per minute, but the same argon I am giving only 12 liter per minute, because it is already in the heavy weight, it is going to go down and it can able to protect. Then why I need to unnecessarily why I need to give more liter per minute? Therefore for argon I am giving 12 liter per minute as usual. But helium having the turbulence effect and lighter, it is trying to move upward. If we want to use the helium, we have to give more protection. It means more force to be given. Then because of the high mass level, it can able to come down and then impinge there. Therefore the protection can be performed. So therefore here helium is given 22 liter per minute and argon is given lighter. It means quantity is argon, it's less, 12 liter per minute we can use. So see, here I am giving 12, but here I am giving 22. More consumption is there. So therefore preferably we can use argon in the downhand portions at all cases. Here helium can be unexpectedly, if we are having the lighter weight, we can able to useful those things in the upward overhead positions. Helium it is consuming more, argon is consuming less. So there moderate arc stability, moderate heat transfer, moderate speed, but cost is less. We can able to generate. Therefore argon is preferable when compared to helium for the downhand portions. So optimum speed. So higher than that of optimum, if you are keeping more than that of optimum, flow rate is more, what happens? Poor arc stability, it's forcing turbines again will form. Increased atmospheric contaminations due to suction's effort. So these things to be taken care. Now we come to CO2. We have seen already this inert gases of argon and helium, and also we should see this active gases of CO2 when we are giving as a shielding gas, generally, in general, not specific for TIG. Carbon dioxide CO2 is the least expensive shielding gas. Helium is costly. Providing the deep penetration, possible. However, it negatively affects the stability of the arc. It means it is going to react active gas. It is going to reaction with inactive gases. Inert gases, no reaction with the atmospheric. But active gases, it is the name tells it is active. It is going to react with the atmospheric. Therefore, when it is reacting with the atmospheric, stability will be spoiled. Shielding, protection will be spoiled. Even though it is giving penetration, here the stability is not there. Current consumption should be high. So stability of the arc enhances the molding method's tendency to create droplets or spatters. Due to this inability of a not stable arc, sometimes this spatter will form. Spatter is nothing but a water metals which is splitting out of the base material after dropping down. We have seen droplets, spray transfer, drop transfer. In such cases, it may comes and goes on the other side, which causes the spatter. Carbon dioxide concentration is of 1 to 2% is commonly used in the mixing of the argon. So what I am doing? I am using the CO2 for penetration, but protection is needed first. Therefore, I can able to do 75% of argon plus 2% or 25% of CO2 we can able to use as commonly this type of category can be utilized. So these things, the voltage we have to identify. The voltage of the TIG welding process is a variable only by type of gas being used and changes in the arc length. The current is adjusted proportionally to the tungsten electrode diameter. See, the current increases, the diameter penetration increases, but the diameter should be constant. Therefore, the current increasing, in case of diameter increasing, we should increase the current factor also. The higher the current, deeper the penetration. You can able to understand, higher the current, deeper the penetration. But the diameter, accordingly, the current should be fixed. Welding current, how much we are doing? The welding current in the range of 3 to 200 amps or 5 to 300 amps, 30, since the ranges. Welding voltage 10 to 24. I told you is 24 volt. For a given current, deeper penetration of the is achieved with the direct current electrode negative. That is what we have seen in the image. Electron flow from negative towards the positive end. The receiver is positive. In such a way, base metal will melt. Additionally, filler wire we are supplying in between. So that is how pure tungsten electrode is a ball tip shape with the direct current electron negative provides a good arc stability. The welding of aluminum, what we are using? I am remembering you. Welding of aluminum takes place by alternating current factors. Provides a cathode cleaning also. Sputtering we name this of the weld pool. Removes the refractory oxides. With alternating current to have sputtering effects, argon has to be used as a shielding gas mixture. Sputtering does not take place with the helium. So helium can also we can use instead of argon. In case of manual GTAW, always argon is used. So how we are initiating the TIG welding processes? TIG welding can be done in two methods. These points we know already. The touch start method, or otherwise the high frequency start method. See, the tungsten electrode, the release of electrons takes place in the sharp points. Somehow it should be in this, you should use this vertex angle. But in this point, sometime it is a chance of breaking of this sharp corner. But instead of this flat point, releasing of electrons finds the easiest point of a sharp corner, but also during it is a high heat point positions, these points will be breakdown. Therefore, what I am doing, instead of a flat, we are going for the sharp. Sharp creates the breaking at high temperature. Therefore, I am converting the sharp into bald end. Too fine angle will promote the melting of the electrode tip. So we are not going for the too fine sharp, but we are not using the flat. Instead of that, we are using the ball ended. So when the welding of aluminum with alternating current, the tungsten end of the chamfered and forms the ball end when this welding process. In such a way, here also, instead of a flat, the electron releasing will be high in the ball ends. So we can use the balls. The electrode diameter, type and vertex angle are all critical factors. Because when the diameter is not changed, simply going for vertex angle of sharpening those things, this release of electrons will be difficult. So considering all these essentials, the vertex angle is fixed. About the tip of the tungsten tip, what I mean, vertex angle we are telling. This angle, we are calling it as a vertex angle. So when it is increased, more sharp we are giving, we know penetration increase, because the electron flow finds the easiest path of sharp corners by which electrons will comes out. But there is a problem here. More heat means this will cut down. Therefore, some other problem. But vertex angles, if it is a sharp or increased, good penetration will done. When the vertex angle is decreased, what happens? In case of, instead of this, if it has this, then the workflow will be form a broader, wider. So width will increase. Sharp point, pinpoint, penetration. Broad point, wider point, it is increasing the welding width. So bit width is increased here. So for now I am using for electrode tip for alternating current or this direct current electrode negative. How to use this? Electrode should not heated, 70% heat to be there, and the sharp point is sufficient enough to break and fall into the molten metal to form tungsten inclusions as a defect. Therefore, what I am doing, I am flattening, little bit small flattening I am doing for the direct current electrode negative. But for the alternating current, I am doing the electrode in the ball-headed format. So it is a reverse heating will happen, alternate heating will happen to the workpiece and to the gun. Workpiece and to the gun due to the alternating current supply. Such cases, we are using the ball-headed tungsten electrode to avoid this tungsten inclusions breaking. Factors to be considered of high current. So our welding current is too high, excess melting will happen sometimes, and also this tungsten breaking. That is what I have told you. So this point is related there. When this it is high, this will break. Actually, point to be like this. The point is here, but the point is we have breaked specifically to avoid this tungsten inclusions breaking. Therefore, we have made this tungsten in this way. Therefore, tungsten inclusions will form when the high current, high melting. If it is low means electrode tip not properly heated. Low current, tip itself not heated, electrons will not come, electron emissions will not happen. This point we know. An unstable arc will form. So I have shown you here few examples of this methodology I want to show you. Welding parameters are the different materials, approximately values for the butt joint I have performed here. Of the butt joint. What I have done for the aluminum, some materials I have given. How much current factors, how much tungsten diameter available, how much the filler diameters, and argon shielding, how much we should give. Aluminum we can provide 200 to 350. 200 to 350. That's the magnesium. 100 to 150, copper 250, 350, mild steel, stainless steel 250 to 350, see. And then this is a direct current straight polarity. It is nothing but a direct current electrode negative. Gray cast iron 160 to 200. By the experiment, by the research, they have some fixed values of aluminiums for various materials are given. This is about the current factors. For the given current of 250 to 350 amps, how much tungsten diameter we are using? Up to 3 mm we can able to use. 350 3 tungsten electrode non-consumable. This is non-consumable. Okay. Non-consumable. What about this one, consumable filler rod, which is we are supplying it towards the middle between the non-consumable and workpiece. So here we can able to use it 3 to 4 mm, 3 and 3, same sizes. So here also 3, 4, 3 variables are there given. Argon gas supply is about 7 liters per minute we are supplying at that fast. 7 liters per minute, 7 liters will not be consumed at that force we are giving. Argon gas flow rate 7 liters per minute we can able to give this concerns. So cathode cleaning process we should see additionally. Important for welding of aluminum and magnesium because it removes the refractory oxides when we are going for the cathode cleaning methods. With alternating power source, the cleaning action of a direct current electropositive and the deep penetration of direct current electronegative both are achieved in this techniques. So with alternating current, generally the argon shielding gas is used for welding. So what we can achieve here? Better arc stability, better cleaning actions, superior weld quality than that with the helium and shielding gases. So with this, when we are connecting to the electrode positive, it can be used for cathode cleaning day. What is cathode cleaning? Oxide layers will form in such cases. The high velocity electrons, when we are coming from the other towards traveling to the negative to positive, it is observed here. It is observed there. At this point, the oxide layers are removed. Likewise, so such things, cathode cleaning can be used in direct current electrode positive. Joining is made difficult by surface formation of refractory of aluminum oxide of melting point much higher than that of the aluminum metals. Therefore I am telling the oxides are broken up by cathode cleaning action. So here our intention is to break the oxides. Because atmospheric contamination takes place and tungsten and the workpiece are oxidized. That we have to break. That is given by the cathode cleaning process. So once broken, they are flowed upon the molten metal and they no longer interface with the welding process. That we can able to understand with this. The summary in welding, we have seen today about the types of TIG. Then also we have seen about the types of shielding gases. In types of shielding gases, we have seen about argon, helium, and then properties, and then also about the active gas of CO2 properties has been seen. The remaining part of the subject we will see in the next session. Thank you.